Hello, it's Mrs. Schroeder again. We're going to continue talking about section 10.4, something new, order and spontaneity. What does it mean to be spontaneous? What is the order of the universe? We're going to talk about something called Gibbs free energy, another one of the thermodynamic properties, along with enthalpy that we've talked about. So we know enthalpy is H. That's one of our thermodynamic properties. The second one we're going to talk about is something called entropy. Now, entropy is interesting because it's a measure of the disorder of a system. We're not talking about energy here, or something that we can create heat with or light with. We're just talking about how random something is. We use the letter S to define entropy. Don't know why. If you used E, it would be energy, so I guess they just changed it. The units, joules per K. K stands for Kelvin. Temperature has to be in Kelvin to do this. The principle behind disorder. All systems will naturally become more random. That's what they try to do. For example, if I have something in a very high concentration, it will try to diffuse. It will try to become more random to be spread evenly across something. Some things that increase entropy. So ways to make things become more disordered means to have a higher entropy. So if I dilute something, it's become more disordered. The particles are farther apart. If I dissolve a solid, it's definitely becoming more random now. Particles can move. If I reduce the pressure of a gas, it also becomes more random because there's more space between the gas. If I have a chemical reaction, so this is if a reaction takes place, if there's more moles in the product side than moles in the reactant, it's more random. If there's more gas particles in the product side than in the reactant, it has become more random. So these are all processes that increase entropy or become more random. Now Hess's law applies to entropy. And we're going to use the easier way of looking at Hess's law, where we consider things that have been measured already. We want to calculate the delta S of a reaction. How disordered or how random, what is the change in disorder of a system? I'm going to use the same table. This is the table you already have that I gave out on that pink sheet. It's also found in your book. You can also look up tables if you need a delta S that you can't find. You can look it up somewhere online. But entropy problems. So we're going to look at your book on page 361. So the first one on page 361. It says, find the change in entropy for a reaction below by using table 4, and delta S for methanol is 126.8. Now my reaction is carbon monoxide plus 2 hydrogen are reacting to form methanol, CH3OH. And the problem says to find delta S. How much has the entropy of or randomness of this system changed? I use the same idea of Hess's law that I just used with enthalpy. Delta S of the products minus delta S of the reactants. In this case, my product, I only have one, is CH3OH, the methanol. I do have 2 reactants, delta S of the carbon monoxide. And if you'll notice, there are 2 hydrogen, so I need 2 here. 2. And we said for enthalpy that it's 0 for enthalpy. It's not for entropy. For entropy, this value is going to have a number, even if it's an element, because all things have some randomness in them. So when I use my table and I look up values on that table for these numbers, I'm going to end up with delta S for the reaction is going to be 126.8. That's not actually to look up. That one was given in the problem. Joules per mole times Kelvin. minus, for CO it's negative 197.6, same units. For hydrogen, 2 times 130.7. I add those together and I get negative 332.2, which means it is becoming less random, or delta S decreases. The negative sign, I'm looking at this negative sign here. Because there's a negative sign, I know it's less random and delta S decreases. So again, we said systems naturally want to become more spontaneous. This reaction would not try to do this on its own. So would it happen on its own? Why do reactions occur? Well, reactions are more likely to occur if the enthalpy is negative for exothermic reactions, because things want to go to a lower energy state. So reactions tend to go to lower energy, and they also like to go to higher entropy. Okay, so we have two opposing things. Sometimes they're opposing. If it's more negative or exothermic in enthalpy, that would be favorable. If it becomes more random, that would become more favorable. So how do we know if a reaction is actually going to occur or not? Well, we have another thermodynamic property, this thing called Gibbs free energy. And Gibbs free energy is an interesting concept because it's not a real thing. It measures the tendency of, or it's a way to relate delta S to delta H. So what's interesting about it is they've come up with a system to really relate enthalpy and entropy in a way that's useful now. So if I can put these equations together, delta G is delta H minus T delta S, I can start to understand how the energy of a system is going to change. Does the ability for the system to do work or to have energy available to do work? And I can calculate if that's going to happen or not. Couple quick notes to pay attention to. Delta H is usually given in kilojoules, and delta S is usually in joules. Just because of the magnitude of the numbers they are, in the charts it's easier to give them in these units. But if we're going to calculate things, we have to make sure the units are the same. Units have to match. So temperature I'm going to change to Kelvin, always. So always in Kelvin, never in degrees Celsius. Change it if you need to. And then you need to convert delta T to kilojoules. How do you do that? Divide by 1,000. Okay, so if you have 100 for that term, divide it by 1,000, you have 0.1 for that term. So always make sure you divide to get to that kilojoules. Now again, I said this relates to them. The reason it relates them together is so that I can determine if a reaction is going to happen or not. Is it going to be spontaneous? So spontaneous reactions are something that can occur without outside assistance. I don't have to go in and force it to happen by changing the pressure, adding some energy to it, forcing it somehow to happen. It doesn't mean it's fast. It doesn't mean that the instant I put those two things together, they're going to react. It just means it is possible. So sometimes you'll hear something on the weather talks about conditions are favorable. We're going to talk about that. What kind of things, where have you heard this term before? Don't you think about that? We're going to talk about that in class. So reaction is spontaneous if delta G is negative. So highlight this. Make sure you know if delta G is negative, it is spontaneous. That means it will happen without assistance. Now, on the flip side of that, if delta G is positive, it will not occur, ever. It won't occur, not on its own. If I add energy to it, I might be able to make it. If it's at 0, there's something called equilibrium, which means it's at that state of flux, like a system of a glass of ice water. Some molecules are freezing, some are thawing. And they're both happening at the same time. That's called equilibrium. The more negative it is, it's going to release a lot, tends to occur when things release a lot of energy. Okay, so things that are combustion might have a higher delta G. It will depend on the temperature. So I can take an endothermic reaction with a positive entropy, and when I make the temperature high enough, I can make it spontaneous because it is dependent on temperature. So this temperature term is more important. The T delta S term is more important at the higher temperatures. And again, that's just because of the way the equation is written. Minus T delta S, I'm trying to get to a negative number. So just a quick example on how this works. Delta G equals delta H minus T delta S. I'm looking for that. I'm trying to use that equation. If you look at your book on page 364, there's a practice problem. Reaction has a delta H of negative 76 kilojoules and a delta S of negative 117. So delta H equals negative 76 kilojoules and delta S equals negative 117 joules per mole K. So what I'm trying to find now is this reaction going to become spontaneous? What's the free energy for this? Remember I said you're going to have to divide by 1,000 to get this number negative to be a kilojoules. Clean that up a little bit. Equals 0.117 kilojoules for every temperature. And delta G for this reaction would be negative 76 kilojoules for the delta H term, minus the temperature, which it said it was at 298.15 Kelvin, times my 0.117 kilojoules per Kelvin. And I have negative 110.9 kilojoules. This is delta G for this reaction. I know it is a negative number. So if I have a negative number, it's going to be spontaneous, which means this reaction can happen on its own without further energy added. Now, I can also apply Gibbs free energy, Pascal's law to Gibbs free energy, and we'll try some of these in class tomorrow to show you how this works. Again, it's the same equation of the products minus the reactants, because from my start point to my end point, it doesn't matter how I get there. I'm going to have the same delta G if I have the same reaction start and ending. So I can use that again. We'll do a couple of those in class tomorrow and see how you do and talk about entropy and enthalpy and Gibbs free energy a little more.